A lot of our understanding about the universe depends on our ability to measure distances, to know how far away is that star, how far away is that other galaxy. And of course, one of the really interesting discoveries that's been made over the last couple of decades is that our various measurements at different points in the universe don't entirely match up. And the error bars are not overlapping. And so there's something strange going on. This, of course, is known as the Hubble tension. And I'm kind of obsessed about the Hubble tension right now. And so I wanted to bring on an expert to talk about sort of the current state of the Hubble tension and how we find our way through to resolve this tension, either in the boring way by sort of fixing some fundamental mistake, or the really interesting way, which is discovering new physics about the universe. So my guest today is Professor Geraint Lewis, who I've talked to in the past. He's a professor of astrophysics at the Sydney Institute for Astronomy, and is just an excellent science communicator, is able to explain these really complicated topics to me, and then I guess to you. And sort of as a bonus, Geraint recently published a paper which had a really clever idea on how we might be able to measure the change of the expansion of the universe over time, and maybe a hack that we can do it earlier than we were expecting. So we talk about mostly the Hubble tension, but also his research, as well as some sort of general advice for how to be creative and well-read in the scientific field like astronomy. So enjoy my interview with Dr. Geraint Lewis. So help me understand, like, what are the tools that you use to kind of wrap your mind around that the farther away things are, the farther we're seeing them back in time, the faster they're expanding away from us? How do you hold all this in your brain?
How? Oh, that's an interesting question. I mean, I've been a cosmologist now for approaching more than 30 years. And so, it's just part of the job. It's kind of like, when you start off and you hear the story about the universe was born in a big bang and it's been expanding for 14 billion years, it sounds like just a story, like a fable that this is how we think the universe behaves. But then, of course, when you do the science and you get into the science and you start to unravel all of the different observations. So, the picture of the expanding universe, it's 100 years old. And there have just been a mass of different observations that all fit together to show that this picture describes the universe. So yeah, it just seems natural to me now that this is the universe that we live in. And of course, we're always looking at the observations that we're taking and asking, does this fit with this picture? Or are there things which might be telling us that this picture is not completely correct?
And it's not completely correct. I mean, the thing that has sort of really revealed itself more and more over the last, say, decade is this idea of the Hubble tension, these different measurements of the expansion rate of the universe measured at different times. So what sort of pushed that into, okay, there's something we don't understand territory for you?
Well, so I have to go back again to my starting days as a cosmologist. So, I started back in 1990 was when I started my PhD. And back then, the Hubble constant was still really uncertain. Throughout most of the 20th century, cosmologists have been arguing whether it was 50 kilometers per second per megaparsec, our unit that we use, or 100. There was a factor of 2. But by the end of the 1990s, the number had closed into this value of around 70. So, people were kind of happy that we understood the expansion of the universe and we had measured the rate of expansion. But of course, we didn't stop when we had measured it to be around 70. People have been doing different measurements and have been getting to more and more accurate values. And of course, in science, it's not just the number that you measure that's important, but it's your uncertainty on that number. Do you know it within 10%, 5%, etc.? So in the 20 odd years since that measurement around 72, everyone's measurements have been getting more and more accurate. Their error bars have been getting smaller and smaller. And there's been this divergence in the value that's been measured. So there's a camp that measures the Hubble constant by using the distance ladder, by basically starting here on Earth and working out into the universe to measure the expansion. And there's the group that uses the cosmic microwave background, which is the most distant light that we can see. And you can get the Hubble constant from both of those. And they both claim that they're now measuring it to really high accuracy, but their numbers are different. And the errors are now so small that that difference is significant. And the big question is this a sign that we don't understand cosmology properly, that one of the ingredients that we have in our cosmological model isn't quite correct? Or is it a more mundane thing, like, there's something gone wrong in the measurement somewhere of how we're calculating the Hubble constant? And people aren't really sure. There are people arguing both ways if it's significant or not. But it is really what our current mystery. It's the thing that keeps cosmologists up at night.
Now, when we build up from the Earth, what is the chain of distances that we're following to get out to? I'm not even sure how far this ladder extends.
Well, it depends on who you talk to, but it extends all the way out into the deepest reaches of the universe. The biggest problem we have in cosmology is the universe decided to make things in different sizes and with different brightnesses. So when we look out into the universe and we see a star, we don't know if that is a dim star nearby or a bright star far away without doing extra work. So the distance ladder, as it's called, is a series of steps that we use to measure distances in the universe. We start with a nearby universe where we can use the simplest of measurements, which is the parallax. That's the fact that a star can slightly change its position depending upon where the Earth is in its orbit. And so we can measure the distances to those stars by using geometry. And everyone's kind of happy that those numbers are very robust. But after that, we have to start calibrating objects. So, and what we mean by that is we have to find a group of objects, a group of stars, say, whose intrinsic brightness we know, and then we can work out how far away they are based upon how bright they appear to our telescopes. And that is, that's been a long journey over a century for people finding classes of stars that we can say, right, this is something whose intrinsic brightness that we really know, and then using those to map out further distances into the cosmos. And of course, it was like 100 years ago that the big breakthrough was made by various astronomers, but Hubble used the fact that there was a class of variant stars, these Cephids as they're known, that they pulsate, and the rate of their pulsation is tied to how bright they are. And he was able to do that first step out into the universe, to the Andromeda galaxy. But also famously as well is that he fell into a trap that we have, is that he thought he was looking at one class of star, but he was actually looking at another. And with that, he had actually got the distance to Andromeda incorrect because he thought he was looking at a particular class of variant star. So this is the kind of tricks that we have to do, is you measure a distance and you find a new calibrator and you use that to measure another distance, and you step out into the universe as far as you can go. And of course, one of the things that we've been doing is using supernova. These are exploding stars that we can see basically halfway back to the Big Bang. And there's been a lot of work calibrating those. And those are our key distance measure, but they rely on all of the rungs out to the distant universe for us to be confident that we've got those distances correct.
And so each one of those, I guess, depends on two things. One, that you're right about its intrinsic brightness, and that the distance ladder that builds up to that point is correct. And that if you're wrong about its intrinsic brightness, if you're wrong about the lower rungs of the ladder, then your estimate, here comes your error bars and they widen again.
Yes, absolutely. So if one of your rungs has a big error bar, you're not certain about the intrinsic brightness, that propagates its way all the way through to all of the other measurements. So everybody's trying to calibrate everything along the way and trying to make those errors as small as possible. But we still sometimes are, we're still sometimes off because there's a systematic error, as they say. We've gotten something wrong there. And again, that can disrupt the entire chain.
And I mean, I've seen some pretty great meta studies about the distance ladder. And I think there are a lot more objects and techniques in this ladder than people expect.
Yes.
Dozens? You've been responsible for a few of them?
Yeah, well, we have to be, kind of careful. There's no one ladder, right? There's a whole host of overlapping ladders that people use.
Right.
And they're tied together with a bit of string, and you hope that this ladder that you've put together is robust enough out into the distant universe. So it's a whole bunch of different techniques. People are always looking at new calibrators out into the universe. Can we use the size of this kind of galaxy, or can we use the brightness of that kind of object? And so people are always looking at a way to get new calibrators. So at the moment, there's people are still digging into the data with these things known as things like gamma ray bursts, which are these exceedingly bright bursts across the universe. Can we turn those into a standard flash that we can use to chart cosmology? So it's a never-ending journey, but it's one of those things where people are always trying to tie down and make sure that the error bars are as small as possible.
I mean, I think about the mainstays, as you said. You've got the parallax, you've got astrometry missions like Gaia, you've got the Cepheid variables, which people understand quite well, and then you've got like type 1a supernovae and as sort of the anchors to this ladder.
Yeah.
But I imagine in my mind this sort of weird patchwork ladder that's made of 40 rungs that's up, and different ones are in different places, but they're all, people are constantly testing the two rungs against each other to make sure that they do line up. But then there's been a bunch more that are. So what are some interesting ladders that have come out recently, rungs in the ladder, that you find really interesting?
Well, there's a few even older ones that aren't really spoken about that much. There's things like surface brightness fluctuations. I'm not sure if you're familiar with that one, but this is essentially that if you imagine that you've got a galaxy. Well, we look at, say, Andromeda, a neighboring galaxy, and we can see the bright stars in Andromeda. But if you look at a galaxy which is further away, that brightness sort of all starts to wash out until they're very distant, and then they're just a fuzzy blob. So in fact, the people have calculated that if you have galaxies and they've got bright stars, you will see a sort of rippling pattern in their brightness, and that pattern sort of diminishes the further away a galaxy is. And so people have been using surface brightness fluctuations, which I think is a really cool method. It's one of my favorite ones to sort of think about, is that you're counting bright stars. And I said the other one, there's been some recent claims that objects like quasars, these exceedingly bright, supermassive black holes with material swirling around, that people are starting to find some sort of trends in their properties that suggest that maybe there's a hook there that we could use those as standard candles. And they're very important because we can see those back to, 90% the age of the universe, we can see quasars. So if we could really say that we could work out their intrinsic brightness, they would really unravel a lot of the sort of details of cosmology. You're getting back almost to the point where you are getting your cosmic microwave background measurements. So you've pushed the ladder all the way out to where the cosmologists are measuring Hubble's constant. So yeah, I said there's lots of interesting objects. I think that though that there will be many more coming on to the table over the next decade or so, because we are getting things like the Vera Rubin Observatory. They're going to be monitoring the sky over and over again. We are going to find new kinds of objects that have properties in their variations that we will think, oh, maybe this is telling us that this could be a standard candle.
And like the Cepheid variable, how it changes in brightness over time, or like there's the double R Alare stars.
Yeah.
What impact has gravitational waves had on this?
Well, again, now this is an interesting question. People are asking whether or not gravitational waves are. They don't call them standard candles; they call them standard sirens, right? Because
Right.
It's a ripply wave, and you can turn it into sound, and it sounds like a chirp, etc. But the thing is that if we imagine that we understand the physics of what's going on in that merger event that creates the black hole, creates the gravitational waves. So often it's a pair of black holes or it's a pair of neutron stars. If you imagine that we say to ourselves, we really understand the physics here, right? Neutron stars are supposed to have a certain mass and they collide in a certain way. Then we can, at some level, work out how much energy is released in that merger event as a total brightness. And then comparing that to what we measure here on Earth, then we can chart that distance out to where that merger event took place. Of course, what we really need to do is we need to tie that merger event to something that we can see. Because measuring a distance to an object that we can't see doesn't really tell us very much. So we need to sort of see these events occur inside a galaxy, so we can also see the starlight as well. And that will allow us to sort of chart across the universe. The problem that we have at the moment is that we've got to get to that stage where we say to ourselves, right, I've seen this signal in the gravitational wave, and from this signal, I know what merged. I know that they were a pair of black holes and they've got this mass ratio and all this kind of thing. And we're not quite there yet, but we're the black hole physicists are telling us that we're getting close, right? That we are really starting to find the fine detail in the sort of gravitational waves that we can see. And of course, with more gravitational wave detectors and always the reducing the error bars, increasing the signal, we will get there kind of soonish. This is what I'm told, at least.
Right. Do you think it has the potential to become one of these gold standards for measuring distance in the universe? Yeah. At the moment, I think so.
It's a question of, again, getting the cleanest signal possible, such that, again, you can say to yourself, I really know what happened in that merger, that it was a black hole of 20 solar masses and a black hole of 10 solar masses, and they merged with this property because that produces this signature. I think, yeah, it has the potential to get there.
So I guess those are some of the parts of the ladder.
Yeah.
And then let's go to the other side, which is the measurement of the cosmic microwave background radiation.
Yes.
And I guess the most accurate version of this is the recent survey from the Planck satellite. What is the technique that the astronomers are using to pull out this expansion rate from that data?
Yeah, so it's a very interesting kind of story, right? I mean, the important thing is that the cosmic microwave background isn't just smooth. So what happened, if you imagine that you had the universe forming, the Big Bang, and just after the birth of the universe was kind of smooth. There was hydrogen and helium and dark matter just spread around. So that stuff was there, but there are tiny ripples in the distribution of material, which come from an earlier epoch in the universe. They come from inflation. And so you've got these tiny ripples there. And what happens, of course, is that if you've got ripples, if you've got more mass in one place than the other, the place with more mass has a stronger gravitational attraction and starts to draw material in. So over the first few 100,000 years of the universe, when it was still hot, it was still a plasma, dark matter sort of started to collapse together to form the seeds of the galaxies we see today. And the matter and radiation basically came along for the ride, right? They get drawn in as well. So it's this hot plasma. So there are no normal atoms yet. It's just charged particles and radiation all bouncing around. The dark matter starts to collapse into itself. The plasma comes along, but starts to bounce, right? So dark matter sort of has this property that it's called collisionless. The material basically just goes through itself. But gas, even in a plasma, they basically can bounce off other bits of plasma. So it's set up these waves in the universe. So there's these ripples that run through the plasma until around 400,000 years after the Big Bang. And at that point, the universe cooled to such an extent that the the electrons could rejoin with the protons and you form the first hydrogen atoms. And that changes the dynamics of the gas in the universe. But those ripples are still imprinted on that gas. And that imprint gets written into the cosmic microwave background radiation. So places where there was more gas, you see at one temperature, and places where there was less gas, you see another temperature. And the differences in the amount of material aren't huge, but they go on to form the galaxies that we can see today. So you can imagine the cosmic microwave background, there's this rippling all the way across the cosmic microwave background, and that rippling is tied to how that material was moving around in the first few 100,000 years. So when we look at the cosmic microwave background from our vantage point on Earth, we're seeing this map written across the sky, but we're seeing it in terms of how big it looks in terms of the angles that we can see on the sky. So some ripples are this big, other ripples are smaller, etc. And so we can actually use our understanding of the physics of the early universe to work out what those ripples look like, to how we are seeing them here on Earth today. And that reveals the expansion of the universe in terms of the rate of expansion, but also the geometry of the universe, because universes can be, they can have different geometries, and what these observations reveal is that we actually live in what's known as a flat universe. And so, the cosmological one is sort of like a single snapshot view of the cosmic microwave background, and that reveals how our universe has been expanding since that 400,000 years after the Big Bang.
So, I mean, I understand that like the overdensities and underdensities that we see in the cosmic microwave background, those are analogous to the giant galaxy clusters that we see around us today. And, they're not the same thing. When we see a big, a slight overdensity in the cosmic microwave background, we know that one day will become a giant galaxy cluster when all of those galaxies get their act together. The part that I have trouble with is like my assumption was always like, okay, we know what wavelength of light was released by the cosmic microwave background radiation. We know how long it's been traveling to us. We could calculate the redshift, but that's not how they're doing this, right?
No.
They're measuring these angles in these anisotropies, in these over and under density regions, and that gets us to the age.
Yes. So imagine that you're near an ocean, right? And you can see waves rippling on the ocean, but you don't know how far away you are from the ocean. You can just see the waves. But somebody comes to you and says to you, "Oh, those waves, they're all 5 meters across." And you say to yourself, now I know those waves are 5 meters across. From the size that I see that wave, I can work out how far away I am from the wave. And
so it's geometry again.
It's geometry again. So in cosmology, it's that geometry of how things look on the sky that tells us how the universe has evolved from 400,000 years to today. But of course, this is dependent upon whether or not you really understand the physics of all that plasma sloshing around in the early universe. And of course, the cosmic microwave background people tell us, yes, we understand that very, very well. And because we see it's not just a single wave that we see. What we're seeing is a combination of waves of different wavelengths, and so we've got so many of this wavelength, so many of this wavelength, so many of this wavelength, and that's what we see on the sky. And actually written into the local galaxy distribution, those waves are still imprinted on the galaxies, the distribution of galaxies we see around us today. So that's why the cosmic microwave background people, the cosmologists, are very confident that we've understood that physics.
Yeah, they seem very certain.
Oh yes, yes.
You talk to them and they're like, "We're right."
Yeah, yes. So they like to point at the distance ladder and just go, "Look at all those rungs that you guys are taking. We've just got this one step into the universe. Right. Look how cool we are."
Yeah. And so on the one hand, you've got this pristine measurement, and on the other hand, you've got this 40-runged ladder with astronomers checking and double checking and cross-verifying and questioning each other's results.
Yes.
And it would be fine if the results matched, but they don't. And
don't.
so here we are, right?
Yes.
So let's go with the boring version of this, which is that somebody made a mistake.
Yes. So we know that people can get fooled in their distance measurement. I'm going to be very careful about the word fooled there, right? I don't want to get across that they're being slapdash. What I want to get across is that these measurements are hard. This is a hard job to do. And people who work in all this calibration stuff, when you read their papers and you read about all of the calibration tests that they have to do, but then you realize, well, they've made an assumption here, and maybe that assumption has impacted something there. And if they had made a slightly different assumption, that would change things. So they said there's this constant cross-referencing, not only up the ladder, but across the ladders as well. And we know that there are systematic things going on. But the people that are proposing that we have a real tension from the distance measurements, they have gone back and they said, they've checked the rungs, and they are confident that the uncertainty that they've put on their measurement of the Hubble constant is correct, right? And of course, the errors are getting quite small, such that even if there's a very small error somewhere, the hope is that doesn't propagate into a big error in the final measurement. But there's still that possibility there, right? I mean, as I said, there are so many checks and assumptions and bits and pieces that are done, and this is centuries-long sort of journey that you need to go check every single step to make sure that people are correct in their measurements.
And is there like a linchpin measurement or assumption that things are resting on? I mean, to go back to your analogy of you're standing up on the cave and you see the waves, and the person says, "Oh, those waves are 5 meters high," and you go, "Oh, okay, then I know how far away they are." And then you go down and you go, I'm just going to double check. And you go down and you're like, "Oh, it's 5.1 meters high."
Yes.
And then they go, "Oh yeah, well, it's close enough," right? You're like, no, that solves the tension right there.
Yes.
By that small amount.
Yes. I would say that there's not a single linchpin, right? In the sense that it could be anywhere along the chain, right? So as you mentioned, the ones that we are most certain on are the geometric measurements, and using parallax and now using Gaia, etc. But all the way out, all the other measurements, people have been beating down the errors, and I said there's always this cross-referencing going on. We know that in places there are some things which do seem slightly out, and people are looking at why that's the case. But again, the Hubble constant people who have measured it through the distance ladder, they're pretty certain that they have nailed down all of the possibilities where there could be a single, right, if this is wrong, then this is going to spoil everything kind of thing. They're very confident that there isn't a systematic error somewhere in their chain. Now, other people have gone and looked at this, and some agree, some have pointed to some places going, well, maybe we need to look at this. So it's not a settled story, but it's not obvious where that error would come from.
I mean, if we had the size of the Earth's orbit wrong, if we, didn't understand the wavelength of, black body radiation from the cosmic microwave background radiation, like either one of those are the foundation of both of these distance measurements, right? But we know the distance from the Earth to the sun pretty well.
Yes. So things like that, the distance from the Earth to the sun, the cosmic microwave background being a black body, of course, what we have discovered is the cosmic microwave background is the most perfect black body there is. It's better than anything we can produce on Earth. And it agrees with the equation that Planck wrote down 125 years ago. So those foundational things, I don't think people are worried about, right? I think at that base level, I think that's fine. But I think the worry might be in, this, the usual suspects of supernova, right? And there's always this big question about whether or not there's evolution in the supernova explosions. And what I mean by that is that in the local universe, we have more of the heavier elements in stars. There's less in the earlier supernova. And does that change the supernova explosion by a couple of percent? Now, again, if you look at the people that write the supernova papers and look at all of the calibration they do, they sort of say to you, look, where is it in here? But you need to go back and keep looking over and over again. There have been lots of proposals about maybe it's extinction, dust in the universe is distorting the view of the distant universe, and people have tested for that and say, no, it can't be there at this level. So again, it's a very complicated sort of story. Again, the picture of a ladder seems kind of nice and simple and linear, but it's not. It's a twisty, turny, messy kind of thing. But it said nothing jumps out as being the single place where this is the source of your error. But there could be systematics in there about the earlier universe is different to today's universe, and maybe that is having an effect.
Right. So then let's go with the more exciting possibility. What could create a change in the expansion rate of the universe at different times that you measure it?
Yeah. So the only if that is the source, then the obvious culprit is dark energy. Okay, so in our standard cosmological picture, we since the end of the 90s, we know that we've needed this component in the universe, dark energy, which is driving the accelerated expansion of the universe. Now, one of the assumptions that is within our standard model is that dark energy is a constant. It doesn't change over the life of the universe. It's the same stuff. It was the same stuff just after the Big Bang as it is today. It's just becoming more dominant today. But some have wondered, what if dark energy is not a constant? What if it changes its spots over the life of the universe? And it doesn't have to change its spots that much. It just changes its particular properties between the cosmic microwave background observations and out to where the distance ladder is reaching, which is roughly half the age of the universe. And then if that's the case, then that means that dark energy is not the stuff that we think it is. It is even more complicated. It is even more mysterious. It leads to even more headaches that it just existing in the universe in the first place. But people are somewhat wary to go down that track. In that, what is dark energy if it can change its spots? Right? If it can, then it is a substance in the universe that we really, really do not understand.
Yeah, I mean, we don't know anything about it apart from being able to measure its presence in the universe.
Yes.
Based on the way it's made type 1a supernovae appear to be moving away faster than they ought to at different times in the universe. I mean, that is not a lot to hang a lot of knowledge on, and yet it is so present, like it's hard to ignore. It's the elephant in the room.
Yes.
And yet it's a very, invisible elephant. So, and it sounds like whatever bizarreness dark energy was up to, it was happening at a time which is very difficult for us to observe in the universe.
Yeah, yes.
After the cosmic microwave background, but before the most distant objects that we can really measure the expansion of the universe on.
Yes, exactly. So this is why one of the things, like if we can get standard candles in like quasars that go back to 90% the age of the universe, then this will shed light on whether or not dark energy was doing something weird in that period and is different to what we think it is today. So who knows? Who knows what it was doing, right? Because we are in Wild West territory in that we have a set of observations, but we can play the theoretical game as fast and loose as we want to, as long as as long as we get agree with the Hubble measurements from the two camps. Then what dark energy could be fluctuating up and down. It could be collapsing and expanding. It could be doing lots of weird things in that epoch, but we don't have the observations to constrain it. So it's frustrating at one level, but it's exciting at another level. So yeah.
But we don't see this happening for, say, 5 billion years. I'm not sure what like the most distant Type 1a supernova is, in the 5 billion.
Yes, it's of that order.
Yeah, light year range. So, as you said, maybe the quasars get you out to 12 billion, which would be great.
Yeah.
And some provisional observations have been made of quasars where people have been attempting to use them as a distance scale. You would, whatever dark energy was doing, it would be sort of wild. And then just as we started to be able to detect its changes, it settled down and stopped this nonsense. That seems weird. That seems convenient to me. So do we see a hint of this in the quasar data?
At the moment, I would say the quasar data is not robust enough to really constrain what dark energy is doing. So the issue is that when you look at a quasar, right, you see a bright dot and it's varying, and people are questioning whether or not its brightness and its distribution of energy and its all the properties. So you imagine that you've got collect all the properties, you put them in a bag and you swirl them around and you try and look, what can I use as a calibrator? And at the moment, there's a little bit of grasping at straws. Is it the slope of the brightness at this wavelength and this kind of thing, without true physical motivation for why that would be a calibrator, something that you could use to standardize your quasars. So at the moment, as I said, it's a little bit fast and loose. I think, though, we are heading into territory where people are starting to truly get a grasp on the properties of quasars, in the sense that we are really starting to understand. I'll be careful with my words. Quasars are complicated objects, so we are starting to understand, what the mechanisms are for producing the energy, etc. So in the future, I'm hoping that what we will find is that we will be able to mathematically predict what a quasar looks like, and then use that prediction to say intrinsically this is what I think this quasar is doing, and I can use this as my distance measurement. But I don't think we're there at the moment.
Right. So let's talk about the new toys then that are coming online, and I want to sort of connect this directly to a paper that you did fairly recently. Let's talk about this idea of redshift drift. Mm-hmm. What is it?
So the redshift drift in my mind, is a beautiful idea. It actually was first proposed by Sandage way back in the 1960s, right? And so the thing is that we live in an expanding universe, which means that the universe today is different to the universe yesterday. But the time scale over which the universe changes by an appreciable amount is long. It's that time scales of hundreds of millions to billions of years for something to really happen. So what Sandage noted is that when we look at a distant object in the universe, we see its light redshifted, okay, due to the expansion of space. But if I come back tomorrow and measure its redshift, that redshift will have changed because the universe will have expanded by a tiny amount more in one day. So the question is how long do I have to wait to measure the change in the redshift of a distant object? And, when Sandage originally wrote this paper back in the 1960s, it was, given our observational capabilities back then, you really are talking about waiting a century, right? So that was an optimistic view. But by the 1990s, things had changed, and one of the things that had changed, kind of perversely, it got nothing to do with expanding universe at all. It's the discovery of planets around other stars, right? So, people measured the presence of planets by looking at the velocity shifts, right? How do stars wobble due to the presence of planets? And there you want to get your velocity measurements down from kilometers per second to meters per second to centimeters per second. And so people were saying, right, with this new technique, I can measure the change in velocity of a star down to these tiny values. And then people realize, oh, well, if we don't look at stars, but look at distant objects, can we start to suggest that we can measure the redshift drift? And so Avi Loeb, back in 98, I think it was, basically rebirthed this topic and said, actually, we can, we are getting to the stage where maybe over 20 years, we can measure the redshift drift, i.e. that the fact that the redshifts of objects in the universe are changing due to the fact that we've got this expansion going on. And so
I was gonna, I pulled some numbers out. I think it was out of your paper, or Brian Corbeline wrote an article about it, and he's fairly knowledgeable about the topic as well. And so he had said that if you looked at a galaxy and you're seeing the light that's taken, say, 12 billion years to reach us, I don't know if this is your information. It would have, it's moving at, say, 90% the speed of light from our perspective, and so you're seeing this enormous redshift, and each year you would be adding about 15 centimeters, I think, or something like that. Over 10 years, you'd be adding like 15 centimeters of velocity per second to this. So you're at 90% of 300,000 kilometers per second, and you're adding a couple of centimeters a year per second to this velocity. That's hard to measure that change.
It is, and so the redshift drift is the redshift drift measurement is not really looking at one object and trying to measure that 15 centimeters per second. What you do is you look at a whole host of objects, right? And so, as proposed by Loeb and some of these experiments that are being proposed, is what you do is you look at a distant quasar, right? Again, so really bright source of light in the universe. And you look at its light, and it will have come through clouds of hydrogen through the universe. So its spectrum has this thing called the Lyman alpha forest. It's all these absorption lines in there. So you can end up with thousands and thousands of these lines. And each of these lines will be shifted due to the redshift drift. So what you try and do is, instead of doing a measurement of one object, you measure 10,000 lines of sight to that object, and 10,000 to that object, and 10,000 to that, and that, and that, and that. And so you hope that you can build up the statistics. So it's not relying on one measurement, but you see the overall shift when you measure the velocities of thousands and thousands of these hydrogen clouds.
It's interesting to me that number, that 15 centimeters per second, does line up kind of nicely to, I think, like, to be able to see another Earth orbiting around a sun-like star, it's like 50 centimeters per year of 50 centimeters per second of acceleration of the star moving towards you and away from you, and that you're in this same regime. And so I could see why people start to go, like, what else could we get done with being able to detect changes in brightness or changes in redshift with that kind of level? And I think, again, if our reporting is correct, when the European Extremely Large Telescope comes online, these are the kinds of observations it could make over a decade, say, of really putting its back into it.
Yes. So this is one of the big exciting things that people are proposing. So we need a big telescope because it's a statistics game, right? That's what it comes down to. And so you want to collect the most signal with the least noise possible, such that you can measure these velocities very, very accurately, right? So they want to put spectrograph on these big telescopes to measure these velocities. But the challenge is not really the cosmological challenge, it's the technological challenge. How do you keep a spectrograph stable for a decade? Because what you don't want is your spectrograph to get, slightly wonky or whatever over that period and basically destroy your measurement. So that is a really big challenge that people have, and it is for the planetary people as well, right? They need the same kind of thing. So the technological challenge of saying that your spectrograph is the same today as it was a decade ago is a really, really difficult problem to solve. But that's why there's big international consortia involving the astronomers, but also, of course, the instrument people, thinking about what it is that we need to do to do these ultra precise measurements over these immense timescales.
And you look at the work done by, say, the folks with LIGO to make these observations of gravitational waves, and many people thought this is not possible for you to detect this small of a change. And yet here we are now, third run into it, each time better and better electronics and technique and mirrors, and they're abusing quantum mechanics to get better data out of this. It's amazing.
Yes.
And so you can see, it's a kind of incredible, like just when humanity puts its mind to these kinds of problems, they really want the result. So, but the prize, what does, we're 20 years down the road and you've got your data, you've got the redshift drift, you're looking at it. What is it telling you? You're seeing the light from the quasars, how those quasars are changing in their expansion away from us. What story would that be telling you?
So, one of the beautiful things about measuring the redshift drift. So firstly, right, it's another handle on cosmology, right? But it's a different viewpoint on cosmology, and it's a very. The picture that you get is you will basically be able to see the expansion of the universe as we go out and look further and further away. And what we have is that as we look at different objects, because the light is taking time to get here, the nearby objects, they are the ones that are accelerating away from us. So we know that their velocities are increasing. The more distant ones, relative to our viewpoint now, are still slowing down, right? We're seeing them when they were in that phase of the universe when it was slowing. So when we get the redshift drift results, what we're going to see is that the nearby objects are accelerating away from us. We actually go through a sweet spot where objects are basically stationary with respect to us. And then further away, we see objects which are still slowing down with respect to us. So that curve that we get, that is going to be an ultra-precise probe of the makeup of the universe. It shows that our nearby universe is accelerating, the distant universe is decelerating, which is what we expect from our cosmological model as we understand it. Or maybe it doesn't. Maybe it does. Maybe it shows something else, right? Like you were saying about what if dark energy was playing up in the first 5 billion years? It would be imprinted somewhere in this signal, right? But it's, the first measurements are going to be like a data point here and a data point here and a data point here. And somebody will say, oh, it's consistent with this kind of picture. But imagine that instead of a decade's measurements, we've got 5 decades measurements, and we've now got a whole bunch of data points. And it'll be the precision curve that goes through that will tell us, is dark energy a constant? Is it changing? When did the acceleration really start? How big was the deceleration, etc.? So it will be a different look at the way the universe is expanded.
So you've got a hack, and this is sort of like the whole point of this whole interview is for us to lay all the foundation about the crisis in cosmology, about redshift drift, all of this to get to your clever idea in the paper that you and your team released in the last couple of days. So what's your clever trick to get us that redshift drift data early?
Okay, so this is a paper that I wrote with one of my students, Cheng-Yi. So we asked ourselves, what if you were impatient? Right? What if you didn't want to wait a decade to make this measurement? Can we essentially make the redshift drift measurement, but with, let's say, a couple of weeks worth of data rather than waiting for 10 years? So we thought, well, what we need to do is we need something else to make up for that time difference. Okay, so we don't want to wait a decade, but can we sort of find a cheat in the universe that has that time difference in there? So what we realized is that we can use gravitational lenses to basically speed up the measurement. So a gravitational lens is where you've got a massive object in the universe, you've got a source located behind there, and you get multiple light paths between the source and us here on Earth. So we can see multiple images of objects out into the universe. And of course, some of the images we've recently gotten from James Webb of galaxy clusters with thousands of lensed images in there, right? So the entire background universe is distorted with respect to how we would have seen it without that cluster there. Now, one of the nice things about gravitational lensing is that the time it takes light to travel along those paths can be different for different paths. So there's this famous way of measuring the Hubble constant, which is looking at the time delay in lensed images. So you look at one image, you see a flash, you wait a year, you see a flash in the other image, and that time delay is tied to the expansion of the universe. And so we said, we don't want to wait, but then we thought, hang on, if we look today, so we look at the light from two images today, and we go back to the source, then that light must have left the source at two different times to arrive today at our telescope. And we realized that those different times, that means that the universe expanded a little bit back then between the two emissions. And so we asked, is the redshift drift written into the redshift difference that we would see today? The two images are slightly different redshifts due to the fact that their light set out at slightly different times. And so
what is sort of the maximum gap that you would get from the two journeys or the end journeys that this light might take?
Yeah.
Years, decades, hundreds of years, thousands of years?
So for a galaxy cluster, and we go big clusters because the bigger the cluster, the bigger the geometry and all that kind of stuff. We are looking at decade scale differences. That's the kind of size that we want. Smaller clusters, you get smaller differences. That makes the redshift difference smaller, etc. You get all the way down to individual galaxies and the numbers become ridiculously small. So we would have to target the big clusters, but of course, that's the kind of thing that people are observing anyway. And so we went through and we basically churned the numbers and asked if we get our 40-meter telescopes and they build the instruments to look for the redshift drift, then you can also look for this instantaneous redshift difference so that you can go out there and we should be able to see it. Again, it's a numbers game in the sense that you're not really going to just look at one object. You're going to have to look at lots of the lensed images and build up those statistics, but that difference should be there. So yeah, we made that proposal and it seems to work. Which is good for Chengi because it's part of his PhD thesis, of course. But yeah, we are now digging into the technical aspects again of what kind of observations you want to make. And so, we in the paper we just had accepted, we're already, how much light do you get from a galaxy? How accurately can we measure the velocities? How big a difference can we see? But it seems to be within our grasp. And again, it's still a 40-meter telescope is still a few years off. So we will refine our approach and hopefully make robust predictions for when the telescopes are actually looking at the sky.
I mean, already, say with JWST, with the JADE survey, they are finding these enormous galaxy clusters. There's this El Gordo one with a bunch of gravitational lenses all clustered around it. And by 2027, the hope should be that they've put in front of you, they've found 5 or 6 really beefy galaxy clusters that have some gravitational lenses that you can use for that. Yeah. I love this idea, even like for the supernovae, where you see this supernovae go off once and then you see it go off again. And each one of these lenses, you can see this thing over time in a snapshot, and the next time it's going to go off. And so if you could see that galaxy well enough, you could see the precursor to the supernova.
Absolutely. Yeah. You're basically getting a time machine for free. This is effectively what you're doing, right? You see something happen and you go, look in the other image, it hasn't happened yet. And in your mind, that seems to break the laws of physics that you should be able to do that. But, Einstein's wibbly wobbly universe, that's the kind of observations you can make.
So what would be, let's say that the entire planet decided the thing they were going to do was solve the Hubble tension. They were going to get to the bottom of this mystery, and they were going to allocate whatever funds were necessary to build the perfect machine to make observations. Do you think that we have the theoretical framework to direct that kind of engineering activity? You know, do you think we know quasars well enough to build a super web, or do you think that we're ready, and if we could just build a JWST with 10,000 meter primary mirror, that would get the job done? Or is there some other wavelength that you would want to look in?
Oh, I mean, that's a tricky question. I do not think that it would be a single kind of facility that you could build that could do everything. In reality, what you would want, if you were really wanted to do this, you would go back to step one, and which people are doing. You take all of the Gaia distances that you've got from geometry, because that we trust. And you go through and you calibrate all of the stars that you've got. So you really know that this star does this, that star does that. And you would redo the ladder, every step of the way, and you would do it with your best facility that you have, and you would make sure that you have, in terms of observations and calibrations, that you nail it at every single step, so there can be no claim that you've got a systematic error here or there, and it's all laid out from woe to go. But that is a big job to go and recalibrate the entire universe. So
you're talking about like a super Gaia, and then some kind of Cepheid variable analyzer, and then a sort of JWST that's able to pick out Cepheid variables in galaxies that are 5 billion light years away, right?
Yeah.
Like that's the...
Yeah, you do that. And then you also then play the game of you find every supernova. So you need to go back and you need to survey the entire sky over and over again. Every supernova you find, you get as much information as possible. So, it's a numbers game. It's a statistics game. It's the story that the media doesn't like to talk about, that there's so much stats involved in science. But that's what it is. It's right. all about how confident am I that this measurement I have made is this number and this uncertainty. And so again, it's all a numbers game.
You advise a lot of people, and a lot of your papers, as I said, I'm looking at your list here so far. I think I see 20 plus papers just in 23. What advice do you have for people who want to become astronomers, cosmologists, who are fascinated by this mystery? What do you think are some productive places to put your energy into it?
Well, so I was talking to some students the other day about this. So I think the key thing about my approach to science, at least, is firstly not to be too blinkered, is to try and see the bigger picture. And by that, I mean absorb what lots of people are doing. The ability to change science by taking an idea from one area and applying it to another. And also the notion that you can take mathematics from one area and apply it to another. And we are seeing this, of course. I don't have to tell people about the growth of AI and things like that. So it's the ability to have a broad view and think about, this problem over here would benefit from me approaching it from that over there. And you only get that kind of picture by not being solely focused in a particular area. So it is that broad view that I encourage in my students. It's not for everybody. Some people like their particular view, but you find that you generally do what everybody else is doing. But the big shakeups come when you can bring something new from outside into an area. And I said we are seeing this all the time. There's been a growth in, again, the media don't really want to talk about this, but the way we approach our statistics in things like astronomy has evolved very rapidly over the last couple of decades, and we are tackling questions that we didn't think we could do because we have a new way of thinking about the data. So yeah, it's having that broad toolkit, knowing what's going on and thinking about what tool do I apply here to basically push this field forward.
I mean, there are a few researchers out there that when I see their name on a paper, I'll read it, because And you mentioned the sort of the idea of the redshift drift, and that Avi Loeb had sort of, Avi Loeb sort of moves in that same sort of world for me, which is just out of the box thinking, just coming up with just going like, what if, right? And then following an idea through till you finish the math, and then set that paper aside and then move on to some other idea. And do you find, like, what does it take to get you excited enough about an idea to throw some time at it and participate? And what role do you typically find yourself playing?
I like to I like to read and ponder where the problems and sort of mysteries are, and then think about how I would approach it. But interestingly, it's a long game, right? There are some problems that I still have swirling around in my head that have been there for 2 decades, and I haven't found the approach to how I would deal with that problem yet. So again, it's an appreciation of where fields are at and what the questions are. And for me, there are many of these sort of places where you hear a story about somebody's done X and it doesn't seem to match what we expect. Have a quick read, have a think, and then store it away. And then it said you never know when you will read something else and think, oh, hang on, I sort of remember a while ago reading about. So again, I like to read broadly, and I like to read outside of my comfort zone, and to get an appreciation of what's going on. I can't say I'm going to solve problems across all of that, but I do like to have that broad view of what's happening, and at least in the astronomy side and the math side as well.
My mom always used to say, like, my mom was like really good at technology, and surprisingly good at technology for somebody who was, previous, generation. And she'd always say, there's got to be a way. And for her, that was very much like, I need to get this document to accept that spreadsheet. And I know that somehow through all of these, right clicking and reading through the manuals and copy pasting, there's going to be a way that this will do what I need it to do. And so it's about discovering the way, and not so much about, the way is there. It's just our job to discover it. And I think that's the kinds of stuff that I trigger on. Like when I'm reading through archive, I'm reading through a journal, and it feels to me like somebody takes a mystery and says, there's got to be a way. Like, here's this thing. We don't know how this works. We don't even know how to get any more data on this. And then somebody says, there's got to be a way. And then that is the seed of an idea.
Yeah.
And I'm sure 99% of the time, people look at it and go, that's not going to work. Like, thank you for thinking that one through, but it's not going to work because of all these reasons. And every now and then someone goes, wait a minute, that's exactly what I need for this thing that I'm doing over here. Thank you for putting in the math.
Yeah.
To give me a way to move forward.
I think there's an aside in there that some people forget about doing science, right? Now and again, you're wrong. And you can go down a path and you think, I've got an idea to solve something, and you're wrong. You get there and it's like, I haven't solved this. But that's not that sort of failure of being a scientist. That's part of the job, is now and again getting to that point and going, but I've never found any path that I've wandered down, I've never found it a waste of time, because you've learned something, you've filed it away, and it will come useful one day.
Fantastic. Well, Geraint, it was a pleasure to talk to you again. Thank you so much for taking the time to explain our modern concept of the Hubble tension to me. If people want to follow your work, buy your books, what's the best place to do that?
Well, I think I'm one of the last astronomers still on Twitter, because I haven't, X or whatever it's called. So I'm Cosmic_Horizons. One day I will move off there and find out where.
Come over to Mastodon. We're having a great time.
There's too many choices now, right? There's Mastodon, there's Blue Sky. I just don't know where to go. So I will get this eventually. I do have a website which I'm getting back into updating, which is just geraintlewis.com. Books are available on Amazon. They make wonderful presents and help pay off my mortgage. So, yeah.
Wonderful. Well, and when you solve the Hubble tension, will you let me know?
I will let you know, and I will also let you know
Wonderful.
if somebody else has solved it because,
Sounds good. Either one.
Yeah,
It's fine.
yeah. You never
Wonderful.
know.
All right. Thank you so much.
Thank you.
A huge thanks to everyone who supports us on Patreon and helps us stay independent and keeps ads at a bare minimum. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Joel Yancey, Antonio Lofilara, Dustin Cable, Just Paul Davis, Vlad Shiplin, Jay Dennis, David Giltonan, Modso, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verabioff, Andrew M. Gross, and Josh Schultz, who support us at the Master of the Universe level. All your support means the universe to us.